This video is about simplifying radical expressions.
When we talk about a radical expression, what we're talking about is something with a root symbol. If I don't put a number in the little crook of this root, right here, then we're going to assume that that is a square root. The symbol, the square root symbol, is called the radical. The number underneath is called the radicand, and the whole thing is called a radical expression. Sometimes we will take a root other than a square root, in which case we'll put what's called an index in that little crook, and that would be the cube root of 27. You'll notice I put this little hooky-doo on my, just because when we're starting to deal with variables and numbers and everything else, I want to know when my square root ends. So the first thing we need to know is, how do we find, or what do we mean when we say a principal square root? So let's take a look at the square root of 25. Well, in general, that would be 5, because 5 times 5 is 25, but it would also be minus 5. But when we're talking about a principal square root, we're saying we don't want the negative unless I put a negative sign in front of the radical. So the negative of the square root of 25 would be negative 5. So if you already have a radical there, and there's no negative sign in front of it, we're talking about the positive or the principal square root. We want to be able to multiply radicals together, and to do that, we use this rule here that says, if you have a product a times b under a radical, you can break that product up as the square root of a times the square root of b. Also, it says if you have two things that are the same radical, you can put them back together and multiply the radicands. So in this case, root 3 times root 5 is root 15. For our next example here, we have root 15x times root 3x squared. So we are going to multiply our radicands together and make one big square root. So 15 times 3 is 45, and x times x squared is x cubed. Now, we're going to use the rule in the other way to simplify this. So 45 has a perfect square factor. It's 9 times 5. And this is like an x squared times an x. So anything that's a perfect square, I can pull out. So the square root of 9 is going to give me 3. The square root of x squared is going to give me x. And then I have my leftovers of 5 and x. So that's how we simplify a radical. Let's do the same thing here for 180 x cubed. So I need to think of 180, and I want its largest perfect square factor. So I know that it is divisible by 9 and 20. But 20 has another perfect square factor, which is 4 times 5. So I'm thinking that 180 is divisible by 36. So 180 divided by 36 is 5. So that's the largest perfect square factor. I'm going to write it above here. 36 times 5. And I'm going to take the square root of 36 and the square root of 5 separately, and then the square root of x squared and the square root of x. So we're going to get 6. That's from that. We're going to get an x, and then our leftovers are 5x. Okay. So the next thing we want to be able to do is to divide square roots. So same kind of thing here. We can either break something like this up, the square root over a square root. We could take the square root of the top over the square root of the bottom and simplify those individually. Or we could try to simplify first and then do that. So let's do it both ways. In this case, I'm going to get 9. Square root of 9 is 3. Square root of y squared will give me y with 1 left over. Square root of 4 is 2 and 1 left over. And then I can see here that I can reduce by a factor of root y, and we get 3y over 2. So I could have also looked at this in here and canceled a y right away. So that would have given me 9y squared over 4. And then taking the square root of each piece, 9y squared, and the square root of 4 would have given me 3y over 2. So same result. We don't have to do it any particular way, but you can take two square roots. You can either simplify under the radical and then break it up into two radicals, or you can just break it up into two radicals to begin with. So let's take a look at this next example. These numbers are a little bigger. I think I'm going to simplify this before I try to take a square root. So 234 divided by 26 is 9. Oh, that's a lot nicer, isn't it? And then x to the 11th divided by x to the 7th, we're going to subtract 11 minus 7 and get x to the 4th. And you'll notice that these y's are just going to go away. So here we're going to take the square root of 9, which is 3, and the square root of x to the 4th, which is x squared. The next thing you want to be able to do is add and subtract your square roots. So basically, we're going to simplify each radical expression first, and then we're going to add or subtract the expressions with equal radicands. This is very similar to adding like terms. They have to look the same in order to add them. So for example, 5 root 12. I'm going to write it up here. 12 is 4 times 3. So this will be 5. The square root of 4 is 2. And then we cannot take the square root of 3. So that's going to give me 10 root 3 in the end, plus 2 root 3. So we have 10 root 3 plus 2 root 3. Those are like, so we're going to get 12 root 3. Now notice when I brought that 2, I took the square root of 4 and I brought that out. Sorry about that. It does get multiplied by that coefficient. So when we brought that out, we multiplied it here. So keep that in mind. All right, I'm going to do that again over here. I'm going to try to simplify this. 72 has a perfect square factor, has a couple. I could think of it as 9 times 8, but 8 also has a perfect square factor. So this is actually going to be broken up as 36 times 2. And 8 I'll break up as 4 times 2. So I've got 20. What can I pull out? Well, the square root of 36 is 6. I cannot take the square root of 2. I call that my leftover pile. If I have 3 a's, that's a squared times a. I can take 1 out, leave 1 inside. For b to the fourth, that's b squared times b squared, so we can take out a b squared, no b's left over, and a c left over. We'll do the same thing here. We've got square root of 4, which is 2. I've got a 2 left over, an a b squared, oops, I got an a left over, and a c. So I have 120 ab squared square root of 2ac minus 28 ab squared square root of 2ac. And 120 of something minus 28 of something is 92. So I have 92 ab squares square root of 2ac. So keep in mind, another quick example here. If I have something like 5 square roots of 3 plus 2 square roots of 5 minus square root of 3, the only two that are like are these two. So we get 5 minus 1, so we get 4 root 3 plus 2 root 5. I cannot add those two together because they're not like radicals. When we have a radical expression, it's not considered good form to have a radical or a root in the denominator of something. So we call that, when we want to get that denominator not to have a radical number, we call that rationalizing denominators. And there's two ways we can do this. The first one is if we have a single square root. So let's say I had 3 over root 2. What we do is we multiply the numerator and the denominator by the radical that's in the denominator. So that's radical 2 over radical 2. That's the number 1. So when I multiply by the number 1, I'm not changing the value, but I am going to change the way that it looks. So this will give me 3 root 2, and root 2 times root 2 is root 4, and of course the square root of 4 is 2. So it might look like we kind of made it worse, but this is what's considered good form when you don't have a radical expression in the denominator. For this next example, what would I need to multiply by? Well, I need to multiply by the square root in the denominator, square root of 5, square root of 5, top and bottom. Again, that's the number 1, so we're not changing its value, just the way that it looks. So this is 12 root 15 over root 5 times root 5 is root 25, or 12 root 15, and the square root of 25 is 5. So basically what we're doing is we're creating that situation where we have that perfect square on the bottom. So how does that change if your denominator is not a monomial, that you maybe have a complex number like 1 plus root 5? Well, that's slightly different, not too much. We do have to multiply top and bottom by the same thing. What we're going to multiply by is what is called the conjugate. So rather than multiplying by 1 plus root 5, we're going to multiply by 1 minus root 5 on the top and on the bottom. We're going to use the distributive property, and I'm going to show you what happens. So let me erase this one. Oh, I don't know that I can. All right, we'll just write small. So on the top, I'm going to get 4 minus 4 root 5. On the bottom, I'm going to get 1. I'm going to get minus root 5 on the outsides and plus root 5 on the bottom. So those are going to add to 0, which was my point. And then minus root 25. That's going to give me 4 minus 4 root 5. 1 minus 5 is going to give me negative 4. And I can simplify that just a little further because all of these are divisible by 4. So I'm going to get negative 1 plus root 5. So let's do that for this one. We have to multiply by the conjugate. And the conjugate in this case, because I have a 2 plus root 3, is 2 minus root 3. If you're familiar with factoring a difference of 2 squares, we're kind of making that happen. Okay, so we've got 7 times 2, we're going to get 14 minus 7 root 3. I'm going to write this one out because I have a little bit more room. We're going to get firsts 4 minus 2 root 3 plus 2 root 3 minus root 9. Oops, I know what that's going to be, and so I already did it in my head and I wrote it wrong. Gotta be careful, huh? Okay, so 14 minus 7 root 3. These add to 0. This is just 3, so 4 minus 3 is 1, and we get 14 minus 7 root 3 is our final answer. Okay, now I briefly talked about this next example, the principal nth root. So when you have an nth root, in other words, you have this little index here, then you're not taking a square root. You might be taking a third root or a fifth root or whatever. So for example, this means the fifth root of negative 243 means, what do I have to multiply by itself 5 times to get negative 243? Well, when we have an odd index like this, if the radicand is negative, we know we're going to have a negative number. And let's think about 243. 243 is divisible by 3. Oh, I'm going to make a factor tree. So you can see 243 is 3 times 81. 81 is 9 times 9, and each of those 9s is 3 times 3. So how many 3s do we have? We have 1, 2, 3, 4, 5. So our answer here is negative 3. Here's another example. Let's say we want the cube root of 54 x to the 7th y to the 3rd. So what you want to remember is we're looking for perfect cube factors now, and 54 is 27 times 2. 3 times 3 times 3 is 27. I'm going to think of x to the 7th as x cubed, and one more x, and then a y cubed. So we're going to get the cube root of 27, which is 3. I cannot take the cube root of 2. That's my leftover pile. I'll take an x out for that and an x out for that, so I get x squared with 1 left over, and 1 y will get taken out. So that's how you do that. Okay, last thing we want to be able to look at is rational exponents. So rational exponents, basically fractional exponents, help us write square roots and deal with square roots that are not necessarily like. So what we say is that when you have a fractional exponent, a to the m over n, you can write that as the nth root of a raised to the m, or the nth root of a to the m. So remember, the denominator becomes your index. So we want to be able to do two things. We want to be able to write rational exponents as radicals, and we also want to be able to take something that is a radical and write it as a rational exponent. So in this case, this first example here, we just have x to the 1/2. Well, the denominator becomes our index, which is a 2. I'm going to write it, but we don't have to write the 2 there. And then the x is the radicand. For 1/3, that's just the cube root of y. Over here, 9 to the 5/2 is either the square root of 9 to the 5th or the square root of 9 to the 5th. Now, I prefer the first one because I happen to know the square root of 9 is 3. So I'm going to work with this first one. And 3 to the 5th is going to give me 343, I believe. I'm checking myself. 243, excuse me. 243. Okay, now I want to write them with rational exponents. So I have to pay attention here. This is my index. So here's my x. It's not under the radical. I have 3y. The index is my denominator, and the 5 is on top. So I have x times 3y to the 5/2. Over here, I have -3. Since this is really just raised to the first, I'm going to have 5x to the 1/4. That concludes this video. I hope that was a good refresher for you.